Okay, so we'll conclude this 2023 chapter of PMNC with the last lecture by Camille.
Thank you. Well, being the last speaker, maybe before we start, I think we should first give a warm round of applause to Mahan and all the organizers for organizing this very nice event. Thank you. And so in my final lecture, so I will first finish the proof of measure equivalence rigidity of mapping class groups due to Kida. And then I want to compare with what happens with right angle ordering groups, which I said are not rigid, but still we can say interesting things about them. And maybe if I have time, I'll also say words about Higman groups, but we'll see. Okay, so let's start with mapping class groups. So where were we yesterday? So we were left with proving the following proposition, which was giving a characterization of curve stabilizers inside the mapping class group. So the subgroup H of the mapping class group. Okay, so I'm always taking a surface with 3t plus n minus 4 positive. So the subgroup of the mapping class group is the curve stabilizer if and only if. So the first thing is that H is non-amenable and normalizes an infinite amenable subgroup, right? Namely, the cyclic subgroup generated by the Dehn twist about the curve. And if you want to get the whole curve stabilizer and not just a subgroup, you have to say that H is maximal among all subgroups of the mapping class group that satisfy this first property. Okay, and so I remind you, so this is not exactly true in the mapping class group, but in a suitable finite index subgroup where, so this was defined. So this is a technical point in a sense, but let me say why I'm doing this. So this is defined as the kernel of the action in homology mod 3. And what is the point of considering this finite index subgroup of the mapping class group? Well, the thing is that this is a fact due to Ivanov, I guess, that if you have a subgroup of this kernel in homology mod 3 that preserves a finite set of curves up to isotropy, then it fixes it pointwise. Right? Or in other words, if you have a subgroup of this that has a finite index subgroup that fixes a curve, in fact, H fixes a curve itself. So you need this technical thing just to make sure that I get curve stabilizers and not multi-curve stabilizers, for example, because in this finite index subgroup, the stabilizer of a multi-curve is always contained in the stabilizer of each individual curve. And so if you take a maximal thing, you'll get the stabilizer of one curve. Okay, but anyway, this is just a technical point. But the key thing is from this condition, getting the fact that you fix a curve. So right, what I need to prove is that the first assumption implies that H fixes a curve, and then the maximality gives you that it's the whole curve stabilizer. Okay, so the kind of arguments I will use is very inspired from Adams' argument in the case of hyperbolic groups. So you need to have an action of the mapping class group on some negatively curved space. And for this, we'll consider the action on the curve complex. The curve graph. Okay, so what are the good properties of the curve graph? So first, Mazur and Minsky prove that it's hyperbolic, infinite diameter. So we have a negatively curved space. One thing that was crucial in Adams' argument was to have a barycenter map. So if I take 3 points on the boundary, well, by hyperbolicity, I can join them by pencils of quasi-geodesics. And this will define me, this triangle should be thinner, I guess. And by hyperbolicity, this will define me a bounded region in the curve graph. Right now, in fact, what Kida proves is something stronger, that there exists an equivariant barycenter map, which to every triple of points associates a finite set of limits. So here there is a subtlety, because so hyperbolicity gives you a bounded region in the curve graph, but since the curve graph is not locally finite, this is not automatically a finite set of curves. Right? And so there is really something non-trivial going on here, and Kida proves this using the notion of tight geodesics due to Mazur and Minsky. But so this is a non-trivial statement, but it's true that you have this barycenter map in the case of the curve graph. And the second thing that we needed in Adams' setting is, and this was proved by Kida and independently by Hammenstedt, is the fact that the action of the mapping class group on the boundary is amenable, is Borel amenable. Okay, so we have two crucial features of the space that are the crucial features in Adams' style argument. There is one thing that's missing, which is that to start Adams' argument, how do we start? So we start with an infinite amenable subgroup, and from this we get an invariant probability measure on some compact space. And the problem here is, again, because the curve graph is not locally compact, the boundary is not compact. So we need also an action of the mapping class group on a compact space to remedy the lack of properness of the curve graph.
So complex is not locally finite.
Yes.
So this possibly or equivalently inside some, basically you have some point.
For this, yes. So the way Kida argues is using tight geodesics. And so if you take 2 points, you have a choice of preferred geodesic joining them. And this is a way of getting finitely many of them. There is another kind, there is a similar statement for three-factor graph in OutFN. There you don't have tight geodesics. But another way of arguing is, and this is my next point, that the mapping class group also acts on the Teichmüller space. And the thing is that you can lift this picture, the Teichmüller space, and then you have a locally compact space, and you can get compactness from it. This is another way of building the various entropy. Either does it via tight geodesics, which gives you a preferred way of choosing some geodesics between the points, in a sense. Okay, so to get some form of compactness, we need the action of the mapping class group on the Teichmüller space, which is the space of all isotopy classes of hyperbolic metrics that you can put on the surface. So it's parameterizing all all the metrics that you can equip the surface with. And the thing is that so Teichmüller space is not compact, but it has a good compactification that was constructed by Thurston, where you add at infinity the space PMF of projective measured foliations. So what is this? What is a projective measured foliation on the surface? Well, measured foliation is just some way of foliating the surface by leaves such that locally you have a chart where the foliation looks like the foliation by horizontal leaves, except that because of the Gauss-Bonnet, you cannot do this without allowing for finitely many singularities. And so in a measured foliation, you allow for finitely many Franck singularities. Okay, so this would be foliation on the surface. Measured means that you have a way of assigning a length to every arc that's transverse to the foliation. And this assignment is invariant along isotopies preserving the leaves. Okay, and projective means that I'm only considering this transverse measure up to homothety. Anyway, so the important thing for us is that there is this way of compactifying the Teichmüller space. And so we have a compact space to start Adam's argument. Okay, so we have the compact space and we have the good negative curvature features on the right side. Of course, we also need to relate the geometry of the two. And to do this, so there is an important theorem of Klarreich that describes the boundary of the curve graph in terms of certain points in the boundary of the Teichmüller space. So when you have a measured foliation on the surface, it could happen that it contains some closed leaf, or it could happen that it doesn't contain. The generic ones will not contain any closed leaves. So you have the partition of TMF into, so the generic ones are called irrational foliations, those that do not contain any closed leaves. And to every non-irrational foliations, you have some closed leaves. And so you have a way of canonically associating to every non-irrational foliations the finite set of curves on the surface, which by looking at the closed leaves in the foliation. And the important theorem of Klarreich is that, so you see, if you have a closed leaf, so you see some curve. There is some curve that's visible in the foliation. So in a sense, this foliation should not be at infinity of the curve graph. It should be, you should associate some bounded region in the curve graph. But if it's irrational, then in a sense, it lives at infinity of the curve graph. And this is what Klarreich's theorem says, that there is continuous equivariant map from surjective map from the set of irrational trees in PMF to the boundary of the curve graph. In fact, we know exactly the pre-image of a point is just you keep the geodesic foliation and you forget the transverse measure. And really, the geometry behaves well. So you have this subspace here made of the generic foliations. And what happens is if you take a sequence of points in the Teichmüller space, so those are hyperbolic metrics. When you have a hyperbolic metric, you can look at the curve on the surface that's the shortest. This gives you a map from the Teichmüller space to the curve graph. And if you have a sequence going to an irrational foliation, then the image will converge to the associated boundary. So you really have a way of comparing the geometries of the Teichmüller space and the curve graph. And I really want to emphasize that this geometric setting is really crucial in many ways. Having a compact space on the one side, a hyperbolic space on the other, with a comparison of their geometry, you have the same kind of setting in out FN. And this was crucially used for many things. You can use this to prove the Tits alternative for mapping class groups or out FN. You can use this. There is the Bader-Fuhrmann theory proving co-cycle superrigidity theorems from a higher rank lattice to this kind of hyperbolic-like targets. This geometric setting is really crucial. Okay. So remember what I just erased is I have an infinite amenable subgroup that's normalized by H, and H is non-amenable. And I want to prove that H fixes a curve. Okay, so let's start our Adams-Stiles argument. So since A is amenable, and I have an action on a compact space, EMF, I have an A invariant probability measure on the compact space BM. Okay, and now there are two cases. It could be that nu gives a positive measure to the non-irrational foliations, those that see some curves. Well, in this case, because to every non-irrational foliation, I can canonically associate a finite set of curves by pushing this measure forward, I get an A invariant probability measure, nu bar, on the set of finite sets of curves. But remember that this is countable. And therefore, when I have a probability measure on a countable set, I can extract the elements with maximal measure. And so I get an A invariant finite set of curves. But I can write I get an A invariant curve because I'm in this finite index subgroup, the mapping class group, where when you fix some finite set of curves, you actually fix each of them. Okay, so you have this A invariant curve, but the goal is to find one which is H invariant. And the only thing you know for now is that the set of all A invariant curves, which is non-empty, is H invariant, but H could permute them. Yes, for now. Okay, but never mind. The thing is, because, okay, so it could be maybe that, I don't know, this curve could be invariant, but maybe this one also is A invariant. maybe this one also is A invariant. And it could be that, in fact, A is acting trivially on this subsurface, and every curve that lies here is A invariant. Right? But the thing is, because A is infinite, the set of all A invariant curves cannot fill the whole surface. And therefore, it must be contained in some proper subsurface of S, which is canonical in the sense you can take the smallest subsurface of S that contains all A invariant curves. So maybe all the curves here are invariant, and all the curves there are invariant, and maybe this one also is an isolated A invariant curve. But the set of all A invariant curves you must still have something in the complement. And now the thing is that to this decomposition of the surface into subsurfaces, you can associate the finite set of boundary curves, and then those orange curves will be H invariant. So you get in this way that there is an H invariant curve. Okay, so you start with the set of all A invariant curves. You look at the minimal subsurface that they fill, and then the boundary of these subsurfaces will be an H invariant multi-curve, but then I can extract every curve individually will be H invariant. Okay, so this solves the case where the non-irrational foliations have positive measure. The second case is when nu gives full measure to irrational foliations, and therefore, by Clareich's theorem, I can view nu as an A invariant probability measure on the boundary of the curve graph. And now I can use the two crucial features in Adam's argument. So there is a case 2-1. Continue. So if the support of nu bar has cardinality at least 3, well, you can use the barycenter map and argue exactly as we did on Tuesday. So because the support of nu bar is at least 3, you can induce a probability measure on the triple boundary, and you can push forward it using the barycenter map, and you get an A invariant finite set of curves. So you get an A invariant curve using the barycenter. And again, because you get an A invariant curve, the same argument as here, say that you actually have one that's H invariant. And you're happy in this case. And finally, if the support of every A invariant probability measure is at least 2, is at most 2, then you get a contradiction to the Borel amenability of the action. Right, because you would have a canonical set of at most 2 points that's A invariant, therefore it should be H invariant. And this contradicts the fact that point stabilizers at infinity are amenable, or in its dynamical version, that the action on the boundary is Borel amenable. Look, this is the same argument. So this is really an adaptation of Adam's argument to this setting of mapping class groups. And this finishes the proof of the proposition. Of course, you need to prove a version of the proposition for sub-equivalence relations, which I won't do, but it's using this language of amenable sub-equivalence relation and normalized sub-equivalence relation that you can translate the whole proof to that setting. Okay, do you have any questions on the proof? Yes, yeah, I can say a word. So right, so for out Fn, you have the same setting with outer space and free factor complex, indeed. So hyperbolicity of the free factor complex is due to Besvina-Fein. For the barycenter map, yes. So the trick is to say that again you have this problem that it's not locally finite, but if you have, so now the points at infinity, there is also a description of the boundary. They are represented by a notion of irrational actions on trees, and when you have three irrational trees in the compactified outer space, you can join them by folding path. So okay, there is no unique. It's not like in the Teichmüller setting, you have a unique Teichmüller geodesic between the two. Here you don't have uniqueness, but you can look at the pencil of folding paths joining one to the other. And an important thing that was proved by Besvina and Reynolds is that transversely, this pencil will not accumulate to the boundary. The only accumulation points in the boundary are T minus and T plus. And you use this, so now you have this, and okay, this is the picture in outer space, and in the free factor complex, you have some bounded region. So you can look at the pre-image of this bounded region, and what are the points that intersect your pencil of geodesics. So now you have only finitely many simplices in outer space, and this gives you the finite set. You could, I think, it doesn't really matter, right? Like you could do this if you impose that the thing is invariant under the order 3 symmetry, but if you don't, yeah. But right. A priori, so we only have constructions of folding paths from T minus to T plus. So you could, if you want to symmetrize the picture, you can look all folding paths in one direction and all folding paths in the other direction. Yeah. Oh, yes. So, right, so this works on the boundary of the curve graph. This is not true on the boundary of the Teichmüller space. Because, right, so if you have a point in the boundary of the Teichmüller space that's represented by, if I draw it as a lamination, just a simple closed curve, then the stabilizer is non-amenable. And Borel amenability of the action implies that the stabilizers are amenable. Yes. Yes, so you're kind of asking for what are the irrational trees. Yeah. So you say that a tree, an action of Fn on a tree is irrational. So you have to give a notion of what it means to not see any free factor. That's
There is this map which actually gets some part of the boundary of the equivalence.
yes. Yes, there is the similar description where there is a notion of a rational tree, which are those that do not see any free factor. And so it's Besvina and Reynolds and independently Hammenstedt to prove that the boundary of the graph of free factors is the space of a rational. Yes, yes, yes. Yes, yes. So we, with Besvina and Gerhardt, we proved the amenability of the action of outfn on the boundary, which, and it's, you know, it's some form of convergence of like you need to target a tree and show that folding paths targeting this tree will eventually coincide in. Yes. There is also this part, which is trickier in like if you know that A fixes a free factor, why does its normalizer fix a free factor? This is also true, but you need an analog of this band of decomposition. Other questions? Okay. So let's move on to rags. I mean, already the you know, the thing that we can, the characterization that we give is already more complicated for our defense. That's not, but you have this similar geometric setting. Okay, so let me now compare this with the case of right angle Artin groups. So maybe, I mean, we already mentioned them, but I should probably recall the definition just to make sure. So if gamma is a finite simplicial graph, so by which I mean with no loop edge and no multiple edges between vertices. So this is my favorite one. Then the right angle Artin group A gamma is the group which is defined by the following presentation. So we have one generator per vertex of the graph. And if two vertices are joined by an edge, then you just declare that the corresponding generators commute. Okay, so first of all, let me recall you that rags are not rigid in measure equivalence. And one reason is because of graph products of amenable groups. So if you have a finite graph gamma and a family of vertex group, one per vertex, so you have one group associated to every vertex. More generally, you can build the graph product of the GVs over gamma, which is, well, so it's the groups that is generated by your vertex groups, and where if two of them are adjacent, you declare that they commute. So you start with the free product of all GVs, and then you declare that GV and GW commute if V and W are joined by unit. Okay, so this is a generalization of rags where right angle Artin groups are graph products where every vertex group is just Z. Okay, and generalizing Gaborio's statement about free products with Jingyin Huang. So this is following Gaborio. We prove that if you have two graph products over the same graph, and if for every vertex, GV is orbit equivalent to HV, then the graph product are orbit equivalent. And in particular, any rag is measure equivalent and even orbit equivalent to any, so A gamma is orbit equivalent to any graph product of countably infinite amenable groups over a gamma. The proof of this is really not that hard. It's like you need to, well, there is a little trick, but you need to start from an action of this group and then try to modify. So you want to modify the vertex action using an orbit equivalent action, HV, to create a new one, in a sense. Okay, there is another reason for failure of rigidity. Which is, in a sense, more geometric. So this is the consequence of the Ornstein-Weiss theorem. So this is kind of an ergodic, an obstruction coming from ergodic theory. There's a more geometric one, which is the following. So to every rag gamma, you can associate a Salvetti complex, which is the complex that you form in the following way. So you start with a bouquet of circles, one circle per generator of one circle per vertex of the graph, so one circle per generator of the group. And then if two generator commute, well, then if you want the fundamental group of this to be the rag, you should glue a 2 torus on the two petals that they generate. So you glue the 2 torus so that V and W become the generators. So pi 1. And more generally, you glue a K torus where K clique, where complete subgraph on K vertices, which corresponds to a copy of Z to the K inside A gamma. And you get something whose fundamental group is the rag. Okay, and so when you look at the universal cover of S gamma, you get something which is which naturally has the structure of a cat0 cube complex, which another way of describing it is you start from the Cayley graph of A gamma with respect to the standard generating set, and whenever you see a square, you fill in with a square. And more generally, whenever you see the skeleton of a K cube, you fill in with the K cube. Okay, so what we proved with Jingyin is that whenever A gamma is not abelian, the automorphism group of the universal cover of the Salvetti complex, which is a natural, locally compact second countable group in which the rag embeds as a lattice, contains non-uniform, infinitely generated lattice. So in particular, since A gamma and this lattice are both lattices in the same embodiment group, they will be measure equivalent. but they're not commensurable because one is finitely generated and the other is not. We actually don't know whether there are examples of finitely generated non-uniform lattices in general, like in F2 cross F2, you would have, but like in the case of the pentagon, for example, we don't know whether these exist. In case of F2 cross F2, thinking about the Exactly. So the construction is exactly this, and you will get things. So those things indeed will have unbounded torsion. So the construction is indeed, so because A gamma is non-abelian, you can find a free subgroup inside A gamma generated by two standard generators. So it's just two vertices in the graph that are not adjacent, right? So for example, this one. And you consider X to be the cover of covering of the Salvetti complex associated to that F2. So what you get is essentially so the bouquet of two circles corresponding to the F2 gets developed into a tree, but the other generators do not. So attached to every vertex, you will have other loops corresponding to the other generators. Maybe some of them are actually form a torus, and maybe if you have a generator that was adjacent to one that belongs to this F2, then what happens is you will have the torus will be developed to a cylinder this way. And now the thing is that indeed, so you have this tree. So then you can take a tree lattice and I want this tree lattice to be label preserving, meaning that it will send horizontal edges to horizontal edges and vertical edges to vertical edges. So lattice in the automorphism group of this tree that preserves horizontal edges and vertical edges. You can give explicit examples. For example, I guess I can write it as the pi1 of an infinite graph of groups, where maybe, okay, let's say all the vertex groups are cyclic groups, and I'm just gonna write their order. Okay, so maybe this edge would be B, and then this edge would be A, and then, okay, I guess something like this. Those two would be B's, and maybe 4 here. You have A's, and so on and so on. Okay, if I didn't mess up, you should have, when you develop, you should have 4 edges at every vertex, and you get and 2 of them are A's and 2 of them B's. So you get this lattice will act on the tree by preserving the labels, and the fact that it's label preserving says that you can extend to the whole space X by extending torus and the cylinders. So I don't know if this is lambda. So lambda acts on X. Yes. Or you can just like trivially, I mean, you want to preserve the, yeah, you're preserving all the other labels and Yeah. So you get an action on X, and then you can take lambda twiddle be the full pre-image in OT of the universal cover of the Salvetti complex, and this is how you build the lattice. And indeed, you will have something with unbounded torsion. It's possible, yeah. I don't know. Okay, yeah. Okay, I don't know this, but I know. So Jingin also has a. I mean, it had like okay. This is not brand new, right? But so Jingin has a similar construction also in when he studied the quasi-isometry classification and rigidity for rags, and it's possible. Yeah, I don't not aware of this. Yeah. Okay, so we have several sources of failure of measure equivalence rigidity for rags. So what can we say? Well, we can still say something about the measure equivalence classification. And the theorem that we prove with Jingin is that if if you have two rags with finite outer automorphism groups, then they are measure equivalent if and only if they are isomorphic. This is the complete analog for measure equivalence of a theorem of Jingin for quasi-isometry. So notice that so this fails if you don't allow if you don't impose the outer automorphism groups to be finite in general, because of these examples of graph products. Pentagon rag is so this one has finite out, but it's measure equivalent to a graph product over the pentagon, where here I would put a z squared. And this is also a rag because you can write it in this way as a right angle Artin group. But somehow the z squares give you, so if z squared is generated by A and B, you have automorphisms coming from sending A to AB. You have transvections coming. Okay, so this example, okay, so there are two things I can say. In this example, this one has finite out, and this one has infinite out, and they are measure equivalent. So if you want the statement in this form, you need both of them to have finite out. Now, currently we are working on, and we think we can, given one with finite out, describe all the rags that are measure equivalent to it. And essentially, so there are two things you can do. One thing is change a vertex group by a free abelian group in this way. There is also another thing. There are it's possible to have a rag that's finite index in another. So the thing is, if you look at the kernel of the map from A gamma to Z mod 2Z, that would send one vertex to 1 and all the others to 0. This kernel will be a rag so this one is obtained from this by taking two copies of the pentagon and gluing them along the star of V. So something like this. But so Jingin has given the full list of finite index RAG subgroups of a RAG with finite out. This is essentially you just repeat this kind of operations. And so what we believe that we can prove now is that if a RAG is measure equivalent to one which has finite out, then essentially it's obtained by repeating these operations to get a finite index RAG subgroup, and then replacing some of the Werther's loops by Z to the n. Yes. Oh. Yes. Can we extend this to graph products? Is that this kind of? Yes, it's possible. So I have an ongoing work with Amandine Escalier where we try to do things. So let's see. So you have to be a bit careful about how to phrase it. And I think, for example, if you take graphs that define RAG with finite out and are square free for now, then if the graph products, so you take two graph products over these RAGs, if the graph products are measure equivalent, then there is an isomorphism between the graphs that sends a Werther's group to a measure equivalent Werther's group. Something like this. I think square free is not necessary, but you need some condition, because I mean it cannot be true in all generalities simply because sometimes you can write the same group as a graph products in two different ways, and so you cannot hope that in general you will have the same graph. But if you put the correct conditions, I believe that there are statements of this. Okay, yeah, let me maybe give the ideas in the proof of this theorem. You'll see that it's very close to the measure equivalence rigidity proof for mapping class groups. And it will also maybe tell us new things about groups that are measure equivalent to RAGs. So there is an analog of the curve graph for a RAG, which was constructed by Kim and Koberda. It's called the extension graph of gamma. So it's the graph whose vertices are the conjugates of cyclic subgroup associated to standard generators. And where you put an edge between two of them if they commute. Okay, so in particular, if you forget about conjugates, put the standard generators with an edge when they commute, it's exactly the graph gamma. But in the extension graph, you also have all the conjugates, and therefore it's going to give you an infinite graph that plays the role of the curve graph in many ways in the theory of right angle Harding groups. So one main difference for us with the curve graph is that you no longer have the Ivanov theorem. So the automorphism group of the extension graph is much, much bigger than the RAG itself, and it's in fact uncountable. But what helps us for this is that Jingin proved that if under this finite out condition, if the extension graph of gamma is isomorphic to the extension graph of lambda, then gamma and lambda have to be isomorphic. So this graph does not completely capture the rag, but it's enough to distinguish between rags with finite out. And this is what we use. And then, the second step is to run the same argument as in Kida's proof that I presented at the beginning of the lecture, where you have to characterize stabilizers of points of the extension graph and prove that the subgroup H in A gamma. So let me give the statement under the assumption that gamma is triangle free and square free, because the statement is a bit simpler in this case, that we have a generalization to all graphs with finite out rag. So a subgroup is a vertex stabilizer in gamma E, for which action, so gamma acts on gamma E just by conjugation. And so what's the stabilizer of a vertex? What's the stabilizer of a standard generator? Well, it's just the normalizer of this vertex, and the normalizer is exactly the star subgroup. So here you have a copy of Z times F2, and this is the full normalizer of the Z inside the rag. So you have Z times F2, and so you see that again, you have a subgroup that is non-amenable, and H contains an infinite amenable subgroup. And if you want the full stabilizer, you have to take a group that's maximal among all subgroups of gamma with respect to the first property. So it's exactly the same characterization as in the mapping class group setting. Sorry? Yes, thank you. Yes. So here, the normalizer of the Z is Z times F2, and I'm saying that whenever you have something like that, it has to come from the vertex stabilizer. And the proof is very similar to what I explained at the beginning, playing with other geometries. So instead of working with the Teichmuller space and the curve graph, we work with this cat0 cube complex, the universal cover of the Salvetti complex, to have some negative curvature. And it has a good compactification called well, we can take the roller compactification, for example, to work with. So we have the same geometric ingredients as in the case of mapping class groups to prove this. Okay, and what is the output of all of this? Is that if yes, it's yes, right, you have the same thing. So you have amenability of the boundary. This is Niblo, maybe. I'm not. I'm not sure of the reference. So this is, you have amenability on the boundary. You also need a barycenter map. In fact, this would be one way of saying you could have the compactification of the roller boundary and the contact graph. Yes. There is also this, Taliafernos has a notion of the regular boundary inside the boundary of the cube complex. It's essentially, in the cube complex, you have flats, and inside flats, you don't have a good barycenter. But so somehow you have two kinds of points. You have the regular points that are outside of any flats, for which you have a barycenter map. And you have the non-regular points, which live in some product regions. And since they live in some product regions, this will force them to be inside some parabolic subgroup. But yes, there is really a similar setting for this. And the output of all of this is that if you have measure equivalence coupling between A gamma and A lambda, then this argument builds an equivariant map from omega to the space of isomorphisms from the extension graph of gamma to the extension graph of lambda, where gamma is acting by precomposition and lambda is acting by postcomposition. And in particular, if they are measure equivalent, then the graphs are isomorphic. And in fact, so this also says something about self-couplings. It says that any self-coupling factors not through the group itself, that would be outness and that would lead to super rigidity, but it factors through the automorphism group of the extension graph. In fact, in the case of rags, the automorphism group of the extension graph is also the same as the extension group of yet another complex called the lean complex of the rag, which is, so it's a cat0 cube complex on which the rag acts with abelian stabilizers. And from this, the kind of statements that you can derive is if you have a group H that is measure equivalent to the rag, then H acts on this cat0 cube complex with amenable stabilizers. So you can, right? So we don't know the full class of groups that are measure equivalent to a rag, but still with this kind of argument, if you have A gamma with finite out, we can say that any group that's measure equivalent to A gamma will have to act on some cat0 cube complex with amenable stabilizers. Not any cat0 cube complex, but one that's really related to the geometry of the rag. And so, okay, we don't have a complete understanding, but we can say things. And so there is some good geometric understanding of what's happening. In fact, if you want to get even more rigidity, so remember when you think about measure equivalence, there are two ways of thinking, either geometrically or more from the ergodic point of view. So this approach is kind of the geometric approach to understanding geometric properties of groups that are measure equivalent to rag. There is a good solution to the rigidity question from the ergodic theoric point of view. So something I didn't tell you yesterday is that when you have a group G that is out in the sense of yesterday's lecture, so every self-coupling factors through the tautological one, then so this can translate as measure equivalence rigidity, but this can also translate as orbit equivalent rigidity for any possible action of G on a standard probability space. So if G acts on the standard probability space in a free ergodic probability measure preserving way, and if H is any action of a countable group on a standard probability space that is free ergodic PMP if the two actions are orbit equivalent or even stably orbit equivalent, then they have to be almost conjugate, so virtually conjugate. Conjugate would mean that there is an isomorphism between G and H and an isomorphism between X and Y that intertwines the action. So that through those isomorphisms, it's really the same action. Okay, the definition of virtually conjugate is a bit technical, but it's essentially a way of taking care of the fact that you might have to pass to finite index subgroup or take a quotient by finite subgroup. But this is a super rigidity for all free ergodic PMP actions of G. The thing is, in the case of frags, you cannot expect super rigidity for all actions, because given a rag, I can build an action that's orbit equivalent to some action of a graph product of countably infinite amenable groups. But you could still hope for rigidity of certain actions. Maybe up to imposing the right ergodicity condition, you can get some rigidity. So for example, Popa proved that, well, he proved much more than that. But one consequence of his deformation rigidity theory is that if gamma is a connected graph, and let's say A gamma non-abelian, then the Bernoulli action of A gamma on 0, 1 to the A gamma is super rigid in the sense that if you take any action of any other group that's orbit equivalent to this one, it will have to be conjugate. So you don't have super rigidity for all actions, but for those that are, so this is typically a super mixing action. This will be super rigid. And with Jingyin, following the work of Monu and Shalom, we dealt with the case of free products. We managed to highlight the right ergodicity assumption to put on the action to get super rigidity. And we could prove the following. So let gamma be be a connected graph such that A gamma has no center, has trivial center. So gamma is connected, and I also need to impose that there is no vertex that is joined to all other vertices. But nothing more. You don't have this finite out condition, whatever. Now consider an action of A gamma, pre-ergodic PMP. But the new assumption, which will be crucial, is that impose that not only the action is ergodic, but every standard generator acts ergodically. And then you get some form of rigidity. So if you have a group H acting on Y, that is, so free PMP, and you need something more than ergodic. You need something that is called mildly mixing, which lies somewhere between weakly mixing and mixing. So this means that for every sequence of elements going to infinity, and for every A which is neither null nor co-null, if you look at the measure of the symmetric difference between G and A, the lim inf should be positive. Okay, anyway, it's some form of mixingness of the action. And then we can prove under these assumptions that if the two actions are stably orbit equivalent, then they are virtually conjugate. And this, in a sense, solves the question of how to find rigidity in rags, but more from an ergodic point of view, where you impose some stronger ergodicity assumption. Mildly mixing means, so if you take any sequence going to infinity, and you take a measurable subset that is neither measure 0 nor measure 1, then if you look at G and A, the symmetric difference of G and A, there will always be some positive measure. The lim inf has to be positive. Okay, we don't know if what. Okay, I don't know if one can do better than this one. But yeah, so. Okay. Yeah, I think I won't have time to say anything. I don't want to start talking about Higman groups in just 5 minutes before the end, so I will stop here. Thank you.
Any questions for Camille?
Yes. I'm not sure. No, we can do extension graph for the link complex. Well, they have the same automorphism group. I don't know about. I don't. Yeah, that's what worked for us, at least. Yeah. Right. But and this is also very interesting, that it gives an action of the mysterious group on the cat zero cube complex. Now we are trying to exploit this, and now we believe we can prove that if you have a group that is, let's say, a torsion-free group that is measure equivalent to a rag, and if you further impose that the measure equivalence cocycle is integrable, the world length of the integrable of the measure equivalence cocycle is integrable, then H will have to be virtually the rag. The thing is, because when you have this integrability assumption, integrable measure equivalence captures finer invariants like growth of groups. And so among amenable groups, Z would be distinguished from the other ones. And so a graph product of amenable groups is no longer a counterexample to this. And so, and when you have this, you have a group that's acting on the link complex with the same stabilizers as the rag, essentially. And okay, there is still some work, but you can use the geometry to get closer and closer to the rag. Oh yes, I can. Let me, okay. Let me draw it for maybe for gamma at the pentagon. So I will define it first as a simplicial complex, not a cube complex, but then I will say, so the vertices are, so you have one vertex per element of the group. So left coset of one is elements of the group. One vertex per left coset of the cyclic subgroup associated to one generator, and one vertex per Z squared associated to an edge. and the edges are the edges, and so it's going to be two-dimensional. The edges and two cells are chains of inclusions. So you get something that looks like this. So you have a vertex for the identity element. It's contained in cyclic subgroup generated by A1, A2, A3, A4, A5. Then you have those Z squared generated. Yes, exactly. Right, so in general, so here it's two-dimensional because you don't have triangles. You have triangles, so it's exactly this. So this defines it as a simplicial complex. But the thing is, so you can view it as a cube complex where the cubes are here. Has a at zero, always has a at zero metric. The lean complex is you can also has a version for more general ordering groups, also for the Higman groups. This is a key geometry that we use in the proofs of superrigidity of them. No, okay. So it's simply connected. It's just I just drew one, but so here there was the identity element, but you also have a vertex for A1. Then you would have a pentagon around A1, where this vertex is the left cosets of A2 corresponding to A1. And in fact, if you take A1 square, it's also an element of the group. You have another pentagon there. It's an infinite thing. So right. So if you want, when you say universal cover, you can say it's the developed complex of this complex of group structure on the right. Yeah, it goes to infinity. And this one.
I think let's thank all the speakers who are present here for this wonderful lectures.